thanks everyone for joining me for this session. It's my second one of the day, so I'm excited to be here again. And this time I'm going to be talking about addressing the transaction challenge in a cloud-native world. For those of you who haven't met me before or haven't seen my talks, my name is Grace Jansen and I'm a developer advocate at IBM in the UK. I mostly focus on cloud-native Java technologies, so anything from sort of the runtime, like looking at sort of JVMs and things like Open Liberty, like cloud-native runtimes, all the way through to open source tooling like MicroProfile, JCON-ONLINE, all the way up to sort of methodologies, design approaches, integrating with cloud infrastructure, so all the way through really. If I don't get around to any of your questions today, then my Twitter handle is here and it will be at the very end of the PowerPoint as well. So it's at GraceJansen27 and you are more than welcome to reach out on Twitter if you don't want to ask a question here, if I don't get around to it, or if you just think of one later or want to find out more about this subject. So feel free to connect on there. Otherwise, please feel free to put questions in the chat throughout this session. I do have it open deliberately, so just in case you guys want to ask questions, I will try and look at it throughout and get round to the ones that I see. So without further ado, I'm going to crack on with this session. So cloud native application development. Why do we care? Why are we so fixated on enabling our applications to really thrive within this environment and make sure that we're gaining all the benefits and advantages of deploying our applications in the cloud? And it's often because of this. Hopefully you guys have seen Toy Story. If you haven't, please take that away as homework because it is an amazing film. In Toy Story, we have these aliens who often have this catchphrase. I've edited it slightly, but it's this excitement of, ooh, the cloud. It's this excitement of the cloud that really, as developers, is what drives us to push our application development towards cloud native infrastructure, cloud native design and development, because we can see the many benefits and advantages that we can gain from enabling our applications to really thrive in this environment and this infrastructure. Things like, for example, cost optimization, flexibility, portability, dynamic scaling, having that flexibility of sort of not being limited to one potential infrastructure or one potential platform, for example, or vendor. So all of these benefits are what gets us excited, and this is why we really want to be striving towards this cloud native manner of designing an application. And to do that, we often look towards methodologies or guiding principles that can help to lay out the key steps or key development sort of areas we need to be looking at if we're going to be making our applications not just barely survive, but actually really thrive in that environment. And a very common one that's utilized is the 12-factor application methodology. And in this, when you take a look, it goes all the way through. If you've not come across it before, check out 12factor.net, and that will go through each of these factors in more details. Or if you head on over to IBM Developer, I've got an article there that goes through each of the 12 factors. You can check that out too. So in this, it goes all the way from sort of starting right from scratch, like how do you have your code base? What about dependencies? What do we need to think about? All the way through to, okay, once we're running in production, how do we monitor it? How are we going to be looking at things like logs, parities between environments? But actually, when we're taking a look at this, what we do notice is sort of phrases like the ones I've highlighted here. So phrases like, for example, treat backing services as attached resources, or execute the app as one or more stateless processes. And what this kind of brings to mind really is often this assumption of, well, if I'm going to be designing and building cloud native, I have to build stateless microservices. But I'm questioning this. Is this really the case? Like, do we have to be designing all of our microservices to be stateless if we want to achieve this cloud native manner of building an application? Is this really the case? So I took a look at various different vendors' definitions of cloud native to see, do they specify that we have to be stateless in this? So I took a look at people like VMware. These people have been in the world of cloud native for some time. They have quite a long history. They're the people behind Cloud Foundry, Spring Boot, Tanzu Kubernetes platform. They don't mention, although they mention things like DevOps, containers, microservices, continuous delivery, they don't specifically mention stateless. Neither do people like Microsoft or Red Hat or even the CNCF. So what this suggested to me was actually it might not be the case that we have to have stateless microservices to be cloud native. So if we are going to have state, how do we do that in a cloud native manner? Why might we need to have state? Firstly, what is the difference between a stateless application and a stateful one? So let's focus on that first point, so then we can progress to the next one of why might we need state in cloud native applications, and then to the final point of, okay, if we're going to have state, how do we do that in a cloud native manner? So the difference between stateless and stateful. And for that, I turn back to Disney, because what could be better than another Disney cartoon? And in this case, it's Finding Nemo. Again, please go home and watch this if you haven't already. Amazing film. The animation is incredible. There's a great TED talk on how they achieved the animation, so check that out if you haven't. It's only about 10 minutes long. So in this, if you've not seen the film, we have a little fish called Nemo, and he gets lost in the ocean, and his dad, the fish on the left-hand side, the orange one, Marlin, goes to find him with the help of his great friend Dory on the right-hand side, the blue fish. So these characters represent a great analogy of what it means to be stateless and stateful. Let's take Marlin, for example, first. So Marlin is a great representation of a stateful being, essentially. So he has a really good memory. He's able to access it quite rapidly. He's able to remember pretty much everything in his life. And what this means is that when he sees events unfolding before him, when he sees things that he needs to respond to in his environment, he's first thinking about, okay, have I come across this before? What are the consequences of doing this action? So he's thinking through all of his memories, his past actions, what this might mean for him in the future. So he can be quite slow to respond to events that are happening or stimulus in the environment around him. He doesn't really jump into much before thinking about it first. And this is more of a stateful microservice, because essentially what you've got here is that slight slowness in terms of accessing that information first before responding, but being able to sort of have that state stored locally and access it quite readily. On the other hand, we have Dory. This is a key point in the story here, so spoiler alert. Dory has a memory problem. Dory pretty much can't remember much else except her name and the fact that she's a fish. So Dory represents much more of a stateless microservice. She's very happy-go-lucky. She just jumps into anything she sees in front of her. When she sees a jellyfish, she thinks it's a great idea to go and jump on it. So she does. She's really quick to respond to events that are happening within her environment, but she's got no memory that she can refer back to know that, for example, jumping on jellyfish might be a dangerous thing to do. So she's a lot more responsive, a lot quicker, but she doesn't have that ability to be able to refer back to previous events that might have occurred. So she's a lot more like stateless computing. So getting into the technical definitions, but still bearing in mind our fishy friends, let's take a look at some more technical definitions. So stateless computing, this is where we do not retain any session information we don't basically retain any of it, and the state of data doesn't get recorded between transactions. What does this mean in terms of our architecture and sort of design and scaling? Well, when it comes to scaling and recoverability, they're both much easier because we don't have to, usually much quicker, because we don't have to think about things like reinstantiating the state into our microservices if one were to go down and we want to bring another one back up to replace it. So it can be a lot quicker for scaling, a lot easier for scaling, and a lot quicker and easier for recoverability as well. Now, in comparison, when we take a look at stateful computing, again, referring back to our friend Marlin here, what we take a look at is actually, this is where we do retain all of the session information. So all of the state of the data gets recorded across all transactions, so every step. What does this mean in terms of architecture and design? Well, unfortunately, the drawback of this is that, unfortunately, the scaling becomes a little bit more difficult, and so does recoverability. It involves a bit more effort because we have to think about things like reinstantiating the state that might be stored within that microservice, and making sure that we have consistency across microservices, especially if we're scaling. So all of this, it just means that it's a bit more effort. It can take a few more steps to be able to achieve similar sort of scaling and recoverability processes. So why then would we want to go for a stateful microservice when stateless, for example, seems to be much more in line with cloud native behaviors and characteristics, like that flexibility, portability, rapid scaling? And it's because we need to take a step back and not just think about the technicalities of what we're building, but actually their use cases. What are our applications designed to do? And often what they're designed to do is a reflection of the real world. Often what our applications do is what we would want to do physically in the real world. Like, for example, booking a holiday, or for example, trying to find information about something. So our applications are often a mirror image of what we'd want to do within society and within sort of the real world. But when we're taking a look at ourselves, our society, the way we live in a real world, we actually live in a stateful world. Let's take a scenario, for example, where you forget your child or your spouse's or your friend's birthday. That's not gonna go well. We are all expected to remember things like these dates of loved ones, of friends, and be able to sort of speak about them and know them off the cuff. We have to have that state stored locally. We can't just rely on a diary to be able to refer back and say, wait, hold on 2 seconds, let me check my diary first to see when your birthday is. We don't live in a stateless world. We live in a stateful one where we're expected to remember important things and facts and information and memories like that, for example. And so when it comes to designing our applications, sometimes it can be more realistic and for us to need stateful microservices as part of this design. This reflects more realistically on the real world and on how we live. I'm not saying that every application that we design that we are shipping to the cloud needs to be stateful, but in some cases, we do still need stateful microservices. So how can we then store state locally when we are looking at sort of particular operations or processes that might involve multiple microservices or multiple components within my application? And traditionally, we turn to something like transactions. Now, what do I mean by transactions? I'm just going to give a brief definition here just to make sure we're all on the same page. So transactions it's just a term really that refers to a group of read or write operations. But the key part here is that this group will only succeed if all of the operations within it are successful. Now, these transactions can impact a single record, or they can impact multiple records, depending on their complexity and what they're designed to do. A very common example of this is booking a package holiday. Again, remember back to if I was doing this in the real world, it would be a similar process, and it's sort of more reflective of this need to be able to store information across the entire transaction, across the state of all data. So in this, when you're booking a package holiday, for example, the reason that often you'll need multiple read-write operations as part of this whole transaction is because to book a holiday, which is a package, you'll often need flights, but you'll also need accommodation, and you'll also need something often like a car hire or taxis, some way of getting around. And so if you don't have a single one of these, then you no longer have a package holiday. You just have a single flight ticket or a single hotel accommodation reservation. So really, this is a great example of showing when you'd need multiple records to be updated, multiple items to be reserved for you and put aside so that you can actually have your package holiday. So when it comes to transactions, more traditionally, in perhaps more traditional applications, we might have used something called the ACID model. Now, we're in technology, we're developers, we love acronyms. So I like to try and make a point of explaining acronyms, or at least trying to go through what they mean, just so everyone's on the same page. I came from a biology degree and it was like speaking Latin when I first came in. So I try and make sure I describe them all. So what does ACID stand for, first of all? So ACID stands for atomic, consistent, isolated, and durable. And really, this is designed to be sort of a guiding set of principles to follow if you want to do transactions for applications that have things like strong consistency and strong isolation. So These key 4 points are really referring to the fact that all changes to the data have to either be performed or not at all. Going back to that idea of transactions, they all have to be successful, otherwise none of them can happen. Consistency, data must be in a consistent state before and after the transaction. This is a really key point about ACID transactions or ACID models, which is this really strong consistency that they allow. Isolated, so no other process can change the data while the transaction is running. Now, although this can be useful in some cases, when it comes to cloud native, this can create a few issues, which we'll go into. And then durable, the changes made by a transaction must persist. And this is kind of the same for all transactions, otherwise there'd be no point in the transaction. So they're either going to go ahead or not at all. If they go ahead, they have to persist the changes. And this is a very commonly used model in terms of traditional applications. It uses something called rollbacks. So if, for example, your transaction can't be successful, it will use rollbacks to be able to sort of undo any actions that have been done as part of that transaction. So what does this mean in terms of, as I said, it's a guiding set of principles. So it doesn't have to be all of these things, but generally they're designed to be the guide you follow if you want to do ACID transactions. And they are intended to give this really strong data validity, strong data integrity and security in terms of your application. In order to use them, sort of ACID transactions, what you'll need is a consensus protocol. So this is what's used to be able to make sure that when we're using this in sort of distributed processes, we need to make sure that they're all agreeing on a state or a decision. And so that's where this consensus, this idea of agreement, comes in. There are various different consensus protocols you can use. So for example, one of the most common is two-phase commit or 2PC, and that's the one I'll be showing in my demo sort of application today. But if you really want to take a look at some of the others, you could take a look at 3PC, so 3-phase commit, Paxos, Raft. There's a bunch of others that you can take a look at and that other people use. Just for simplicity's sake, and also because it's one of the most common, I'm just using 2PC in my example today. So let's take a look at what happens if we were to use something like an ACID transaction, but in this case, in a distributed cloud native application. So I'm going to use the holiday booking example because it's a really great example that's very clear for us to understand because many of us have booked package holidays. So in this, we have some kind of front end that's essentially making the request. It's then going through to this two-phase commit coordinator. So this is our consensus protocol going on here. And then this is what's essentially used to be able to direct out the various different micro requests or micro transactions to the individual microservices involved in this overall transaction. So we have a microservice for flight, a microservice for hotel, and a microservice for our taxi booking. I'm going posh, we're going taxis rather than car hire. So in this particular transaction, what's going to happen in this first phase is my request gets sent to the coordinator, and the coordinator sends out those individual requests to the microservices. Now we get our resource locking. If you remember back to those ACID principles, and you remember that isolation point, this is why we have to resource lock, because we have to make sure that nothing else, no other transaction, is able to affect those resources whilst we are carrying out our transaction. And this is where it can get a little bit sticky in terms of cloud native. But let's carry on for just now. So in this, we've locked our resources, so now no other transactions or requests can access these. We then send a response back to the two-phase commit coordinator, depending on if we have the resource available or not that the transaction needs. So we're going to take a look at two scenarios. One scenario is an ideal world where all our resources are available. Cracking. The other scenario is a more realistic scenario, especially in the current climate, where we do not have a resource available. We're going to see what happens for both. So in this scenario, as I said, all resources are available. So the response back from each of those microservices is that they prepared the resource, they're all ready to go. So they've reserved that resource for our transaction. So now our two-phase coordinator commit coordinator can essentially say, right, everyone's happy, everyone's got a resource, we're all ready to go. So can you all now go and commit that resource to this transaction? They commit the resource, they send a confirmation message back to that central coordinator, and the coordinator is able to send a message forward to that front end system that essentially says, yep, all good, we were able to book your holiday, all available, please pay us. They pay and everyone's happy. Great. But what about a more realistic scenario where we at least have one resource that's not available, which is far more likely at the moment? And because of the current climate, I've chosen flights to be the one that isn't available, which is probably likely at the moment. So in this, instead of getting a prepared message back from the flight microservice, we instead get a not available message. So now, because it's not, there's no consensus among the individual read-write operations, the individual microtransactions, we aren't able to go through with the whole transaction because not all of them can be successful. We can't get a flight, we can't get a package holiday, because we just end up in whatever country we're from, not being able to get to that other country and have our hotel and accommodation. So in this, we're now going to send back an abort message, and now we're going to free up those resources again because we can't go through with this transaction. And we're going to send this failure message back to that front end system to let them know, I'm really sorry, but we weren't able to get your package holiday because at least one of the resources wasn't available. Now, although this is the correct thing that it should have done, and these scenarios theoretically could work in a cloud native environment, there are several issues with using an ACID style transaction model. First of all, it's pretty slow, or at least it can be. All your services have to wait for the slowest service to finish its confirmation to be able to proceed. So essentially your overall performance of the transaction is really bound by the slowest service within your application. The two-phase commit itself can be pretty slow because you've got to rely on this quite a lot of communication. It's quite a chatty protocol. And you've also got this dependency on the coordinator. So you can have things like scalability and performance issues, especially when you're using microservice-based architecture and you have multiple services involved. Another key issue is two-phase commit protocols, which, as I said, is one of the most common consensus protocol used, is actually not supported in NoSQL databases. So if you're using things like Kafka, RabbitMQ, those kind of like message brokers, for example, and other NoSQL databases, you won't be able to use this because you can't use the two-phase commit protocol. So that can't be applied. That's an issue. Other issues, for example, are now that you're in a distributed environment, we're not reliant on sort of local communications. We're now reliant on network communications to be able to deal with the chattiness between the central coordinator and those individual microservices. So what happens when this goes wrong, for example? How do you know if that microservice received the request from the coordinator? How do you know if the coordinator was able to receive a confirmation message or a response back from those individual microservices? Messages can easily get lost in network communication, and so this is an issue we have to think about and sort of design for. Another one is, because we're now in a distributed sort of cloud native infrastructure, we have the possibility of microservices failing, going down, becoming unresponsive, all of which can be fairly likely in these kinds of environments. So what happens when they aren't available all the time? And this isn't always possible in cloud native applications. Well, how do you know if, were they midway through reserving a particular resource? Did they already send the message? How do you know, how do you bring back up their state? How do you know where it was in that particular microtransaction? So this can all be an issue. And as well as that, you have the potential for that central coordinator to go down. Really, the onus of the transaction is on this coordinator node. So it can potentially become a single point of failure or a bottleneck within our application. So if it goes down, it can be a potential point of failure because your microservices might be waiting on a response back from it. They might still be locked. And if they are still locked, then other app resources or other transactions that are trying to access those same resources won't be able to because they are locked because of that strong isolation. So we've essentially designed a non-responsive application here, or one that is potentially delayed because or has low performance because of the fact that we're now waiting on this coordinator node to come back up, to regain its state and to sort of finish off that transaction. So these are all issues that we can come across when we are sort of, if we want to lift and shift a more ACID style transaction model into cloud native distributed environments. So instead, what we can look at is alternative transaction models. An example of those is something like the Saga pattern. Again, we love acronyms. So what is the Saga pattern? Well, Saga is actually, it's still a failure management pattern, but this time it is specifically designed to help establish consistency in distributed applications. So it's really got that cloud native app in mind. It helps to coordinate those transactions, especially when you've got multiple microservices involved, and helps to maintain that data consistency whilst those transactions are occurring. It is still, like the ACID model, it is still a sequence of local transactions, and it has the same sort of rules about they all occur or they don't occur. However, it's using a different underlying set of principles. So instead of using the ACID principles like atomicity, consistency, isolation, and durability, instead, what we're using now is something called BASE. Again, we just love acronyms. So BASE stands for basically available, soft state, and eventual consistency. So the reason that I've striked out in this comparison the consistency and the isolation is really because it's these two key principles that are arguably the biggest difference between these two models, because we no longer have strong consistency, we now have eventual consistency. And we no longer have this strong isolation. We now have a much softer state in terms of enabling other resources to be able to access those microservices whilst that transaction is still going on. So really the underlying principle in terms of the architecture is slightly different because you don't have this strong consistency or this strong isolation. So when we're looking at things like where our application would sit in things like the CAP theorem, we're looking at being more aligned with something like an AP system, because we are now eventually consistent and not having that strong consistency. If you've not come across the CAP theorem before, I definitely recommend checking it out. There's lots of resources online that will enable you to read up more about this. But essentially what this theorem states is that we can't prioritize all three of these individual factors. We have to be somewhere in the middle, compromising on at least one of them. And so that's where these acronyms of CA, CP, and AP come from, depending on which factor you end up compromising on. So in this case, we can't have strong consistency because we are prioritizing availability and partition tolerance. So we're more aligned with an AP system. Definitely go check it out if that's interesting to you. So now that we've taken a look at the Saga pattern, let's see it in action and see how our different scenarios would work given this new type of sort of underlying principles for transactions. So in this case, again, I'm going to go through the two scenarios. One is where all the resources are available. The other is where we have at least one that it isn't available. And in this case, you'll notice that I don't have a central coordinator. That's because there are multiple different ways of orchestrating a Saga pattern. You can have the orchestrator approach or the choreography approach. This is more aligned with the choreography approach, which I will explain after this. The reason I'm showing this approach is just because it can be a bit easier to follow in terms of less boxes on the screen. So in this case, we're still doing our holiday request, this time with Saga. So what I'm going to do is the first thing I'm going to try and book is the taxi microservice, so the taxi booking. So I'm going to send a request to that taxi microservice from that initial sort of front end system. And what I've got here is, yes, I've got a taxi available. I'm going to reserve that for this particular transaction. And essentially I'm going to start taking the money. And what you'll notice here is that we've now reached this sort of state of inconsistency because I've temporarily reserved this taxi for my transaction, for my holiday, but I don't know yet if there's accommodation available or if there are flights available. So at the moment, I'm in an inconsistent state because I have a resource sort of allocated to this transaction without the knowledge that the other resources will also be available and are also assigned. So this is where we have to compromise on consistency so we can have availability. So then we're going to send a request to the hotel microservice. That's all good. And because we're in an ideal scenario here, an ideal world, our flight is available too. So we can send a confirmation message back, take our payment, and the holiday is booked. Everybody's happy. What about the more realistic scenario where we don't have our flight available? We're all intelligent people. I've skipped the first few steps because I didn't feel like we needed to go through them again. So you get the idea. The taxi is booked and the hotel is booked. And now we're going to try and book the flight to go alongside this. But unfortunately, we now live in a more realistic world where unfortunately the flight is not available. So because it's not available, we now need to, again, just like with ACID transactions, because we can't go through with all of the microtransactions, the overall transaction can't be successful. So now what we're going to do is we need to cancel the hotel booking, and we also need to cancel the taxi booking so that we can essentially go back to where we were and have this consistent state of, right, we can't have this holiday So we need to free up those resources again. So now everything is cancelled again, and we can send a message back to say, I'm really sorry, but we couldn't book your holiday because at least one item in it wasn't available. The difference here is that this is what we call a forward strategy. That's what Saga is. It doesn't use things like rollbacks. This uses something called compensating actions. And so this is where we sort of get into like, it's more forward strategy rather than anything else. So in this, what you'll see is the items in blue are the original actions in a potential transaction of some kind, and the yellow items are the compensating actions. And really, it's up to you to decide what your compensating action will be, what logic you put in there. But often what it will do is essentially the opposite of the action, but it doesn't have to be, it's completely your choice. So in this case, when we book a seat, our compensating action will be to unblock the seat. If we make a payment, the compensating action would be to reverse that payment. And if we allocate a seat, we need to move that seat back to the pool. So this is really what's utilized in these sort of cancellation arrows that I have here. You'd have these compensating actions going on. Another thing that I mentioned with this is that there are different ways of coordinating sagas. There's one which is choreography, and there's one which is orchestration, and it really depends on your implementation of Saga as to which one you'll be utilizing, as well as your application, because it might make more sense if you have, for example, less microservices involved to go with a choreography approach, because it can often be, it doesn't get as complex and it can be quicker and you don't have this single point of failure. However, if you've got lots of microservices involved, then it might be more worthwhile going down the orchestration approach. So it really depends on the tools you're using and also the application you're designing. Now, the example I gave was more aligned with something like a choreography approach. So this is the first approach you could potentially take a look at or use. And this is where there is no central orchestrator. So each service that's participating in the Saga basically performs their transaction and then it publishes an event. The other services that are involved in that transaction then act upon these events that are published, and they then perform their transactions. They may or may not publish other events. It depends on if there's anyone else in the Saga, if there's other microservices they need to inform. It's really up to you how you design that business logic. But the sort of main difference here is the fact that there is no central orchestrator in this. So as I mentioned, this can be better if you have fewer microservices involved, if you've got quite a simple transaction, because it can be quicker in terms of actually getting those messages through. Because if you think about it, when you have a central coordinator, you've got double the amount of communication to be thinking about and to be waiting on, whereas this is just straight through. So it can be a bit quicker. However, it can get quite complex quite quickly. So if you have lots of microservices, I wouldn't recommend going down this kind of approach because it can get very complex very quickly. And so it might be more worth looking at the orchestration approach. Now, the orchestration approach does have a single orchestrator, and this manages all the transactions and helps direct services to the various different local transactions or microservices that you might need. So it basically acts as the central controller for all of the local transactions and helps to maintain the state or the status of the complete transaction. So it's a lot more similar to the ACID, but remember, we're still in the base principles here. So we've still got that eventual consistency and we haven't got that resource locking. So it's a lot more designed. It's designed with sort of distributed cloud native applications in mind still. There's also sort of inbuilt the fact that, you do still have this central coordinator. It could potentially still be a central point of failure or potential bottleneck. However, there have been sort of mechanisms put in place in tools that utilize this approach that sort of account for that and help to mitigate the potential impacts of that, rather than what it was in ACID transactions. So this is the second approach you can use, which I would recommend if you are looking at multiple microservices involved, a more complex style of transaction. So now that we've taken a look at sort of the fact that we probably don't want to lift and shift our traditional ACID style transactions, we probably want to be looking at other patterns for transactions like Saga, for example. And we've looked at sort of the various different elements we need to be thinking about when we implement something like Saga. How do we actually go about doing this in our applications? So I love open source, and so I'm plugging an open source tool to use for this, but there are other tools that you can utilize from various different vendors. So it's really up to you as to how you implement Saga, but this is just one way you can do it. And the great thing is it's free. So MicroProfile. If you've not come across Eclipse MicroProfile before, then essentially this is an open source project that really it's held under the Eclipse Foundation, and really it's been designed for the community, with the community in mind, and it's designed by the community, which is the great thing. It is designed to help those who are developing enterprise Java applications to design for things like microservice architectures. It's all open source, and as I said, it's developed by a wide range of individuals, including individuals themselves, organizations, and vendors who all collaborate together to create this specification and help bring microservices and innovation to the enterprise Java community. There are lots of different contributors in terms of vendors. You can see many of the logos here from various different companies who are involved, and many of them produce implementations of MicroProfile, which you can see here. These aren't a complete list, this is just some examples. The important thing to think about here with MicroProfile is that when you are, if you want to use MicroProfile, it is a specification, so you will need an implementation to actually make use of it. And in terms of implementations, in terms of using MicroProfile, you can have implementation specific factors involved as well. So really, it can be quite specific to the implementation you're using. So things like Open Liberty, for example, is an implementation of MicroProfile, and that's the project that I helped to work on and deliver in IBM. This is, again, all open source, and we have a great website where you can find a lot of guides if you're interested in sort of having a go at this yourself. We also have a blog on here, which I will link to later, which goes through our LRA example. So MicroProfile is a wide range of different APIs is what it offers. So the bottom pyramid here that you can see at the bottom here, this is the standard stack that comes as standard as part of MicroProfile. And it includes loads of different really helpful APIs when we're looking at distributed microservices. Things like being able to monitor the health and particularly application metrics when you have distributed applications in production, being able to have external configuration, for example, and also being able to do things like document our APIs using a standard. Now, as well as the standard stack, the most recent of which is 5.0, which is out, but 6.0 is coming, so keep your eyes peeled for that. We also have standalone projects that the MicroProfile community helps to develop and deliver. And that includes things like for reactive applications, if you want to use GraphQL, and it also includes things like LRA. If you are interested in finding out about any of these particular APIs, we'll be covering at least 4 of them, if not more, in our workshop on Friday. So do come along to that if you haven't already signed up, if you'd like to know more about MicroProfile and really how we can build applications that are able to thrive in the cloud. But the one I'm going to be focusing on today is this LRA API. Again, we just love acronyms. So LRA stands for Long Running Actions, and it is a standalone project from the MicroProfile community. So what is MicroProfile LRA? Really, this is designed with loose coupling in mind, designed for cloud-native microservices. It is based on the Saga pattern, and it uses those more relaxed sort of base style guiding principles rather than ACID style transactions. And it is designed to help you coordinate long-running activities, long-running actions, hence the name. So it's really designed, and the reason it was made and produced is to help Java developers who want to have no strong coupling between services, but that still want to be able to ensure, for example, that they have error handling when multiple services are running as part of a single transaction, ensure that execution of compensating actions is carried out. So this forward strategy is part of the Saga pattern. Rather than rollbacks, we're using compensating actions, and to allow actions to finish early. So these are the main goals. In terms of utilizing LRA, as I mentioned, MicroProfile is a spec, so you will need an implementation. So in this case, we're using the Open Liberty implementation. And for this, Open Liberty actually uses the Narayana implementation of the LRA specification. So this is more aligned with that orchestration approach. So we have a central coordinator and we have participants. So those are the 2 parts of LRA if you want to use it in Open Liberty with MicroProfile. So the coordinator is the one that handles essentially determining the LRA processing, it handles the initialization of the LRA and helps to enlist services that are needed as part of that transaction. The LRA participants, which they tend to just be applications that use MicroProfile LRA to involve themselves in an LRA. And you can involve them in different ways depending on how you set it up. So if we want to actually go ahead and utilize this, we have an example for this. As I mentioned, there is a blog, and we also have a GitHub repo with an example app. So if you want to check that out, the link is at the bottom here, or you can just go onto the Open Liberty site, go to our blogs and search for it. But essentially, the first thing we need to do is to utilize our sort of, in this case, we're using Maven. So this is our server.xml file. And essentially what we need to do is make sure that we've added the MicroProfile LRA feature. Now, one thing to remember is that, so with MicroProfile, you don't have to, the nice thing is it's modular. So you don't have to add all the features if you don't want to. You can just add them individually. The one thing I would say for, if you want to have a go with this, for MicroProfile LRA is there are 2 dependencies that you'll need if you don't have sort of just the standard stack as a feature. So you'll need CDI and you'll also need JAX-RS, which is why they're listed here above the MicroProfile LRA feature in my sort of screenshot here. But all you need to do when we've got this feature in our server.xml is essentially run the coordinator with the command start LRA coordinator and then run LRA coordinator. So it's fairly simple to get started once we've got it set up. Now, in order to ensure that we've got participants to join this LRA, we'll need to use these various different annotations, which is sort of a very common underlying sort of feature within MicroProfile specs is to use annotations. So you'll see it in most of the MicroProfile specifications, annotations used throughout. So in this, we've got 3 basic annotations, at LRA, at complete, and at compensate. These are the bare minimum that you'll need if you want to get started with this and use it in your application in your participants. So the at LRA is the annotation you'll need to enable an application to either join or create an LRA. And then we've got the at complete, which as the name suggests, is basically the business logic of what you want to happen if that transaction is all successful. And then we've got at compensate, which is what you want to happen if, for example, any of the microtransactions fails, and so the overall transaction can't go ahead and fails. So these are the 3 basic acronyms that you'll need. And when we're adding them into an LRA participant, it will look a little bit like this. So this is the same class, but just to make it a bit easier to fit it all on one slide, I've just cropped various different screenshots. So you can see at the top here, we have the at LRA annotation, then we have the at complete annotation and the business logic in that, and the at compensate and the business logic associated with that compensating action. Now, what you'll notice is in the at LRA annotation, I have this type, which is LRA.type. In this case, I'm using the type required. Now, I mentioned that there's various different ways that you can get a participant involved in an LRA. You can either get them to always start an LRA, or you can get them to either start or join one, depending on if one exists, or you can get them to just join one and never create one. And that's what this type does. So required is sort of the middle one. So this is where if an LRA doesn't exist already, we'll create one. But if an LRA does exist, we'll just join that one. If we want to always make sure we're creating one, we need to use the requires new type. Or if we want to make sure we're never creating one, we'll have to use the mandatory type. So these types help to specify how your services can interact with that LRA and either create it or join one. Now, I mentioned that those aren't the only annotations you can use, they're just the basic ones. So if you do want to go into more detail on sort of what other annotations you can use, I'd recommend checking out the MicroProfile documentation. They've got some great information there, really goes into detail on each of these annotations and how you can use them. But the additional ones that I haven't mentioned so far are at forget, at leave, and at status. So these are additional annotations you can use. At forget is essentially there in case you need to release any resources that were allocated as part of an LRA. So that might be part of a compensating action. There's also things like, for example, at leave, if you want a class to leave that is no longer interested in an LRA. So let's say like I no longer want a taxi, I'm just going to walk everywhere. I then don't want that to be part of my transaction, so I can use the at leave to get that to leave. and then at status if we need to report the status at any point. So as I mentioned, this is all part of a demo app that we have. So if you want to check that out on GitHub, feel free to. It's all open source. And if you have any suggestions on how to improve it, please feel free to open an issue or create a PR. We love it when others contribute and help us to create these examples and make them better. So feel free to check that out and help us in any way if you'd like to. So that is my whistle-stop tour of sort of cloud native transactions and how to use them using open source tools like MicroProfile. Hopefully, in summary, what I've shown you through this presentation is that stateful microservices are often still needed in our cloud native world for specific types of applications, but that traditional transactions aren't really suitable for the cloud infrastructure and for this sort of distributed style of application. But luckily, we have alternatives like, for example, the Saga pattern and open source tools like MicroProfile LRA that can help to provide us with alternatives for cloud native applications and microservices. And the nice thing is a lot of them are open source, so you can try them out for yourselves without needing any proprietary licenses or anything. In case I haven't given you enough resources already, here are some links to some of the things I've mentioned throughout this presentation. The blog that I mentioned that goes through this step by step. Also the GitHub example, in case you missed it on the other slide. I've also got a link here to the MicroProfile specification, which goes into LRA in more detail. And also down the bottom, if you've not come across Saga before and want a recap to refer back to, that's a great recap that you can go and take a look at or share with your team or refer back to. If you want to check out more about the open source projects I've mentioned, I've also put links here to the various MicroProfile sort of a good documentation, for example. I've got a what is MicroProfile series if you want to go into that in more detail or find out more about the other specs that I didn't mention or go through, or you can pop along to our workshop and we'll go through it more then. And we've also got the Open Liberty links here as well. So thank you so much for listening and sticking with me throughout this presentation. I'll take a look at questions now quickly. I think I have about 3 minutes. And if I don't get around to them, feel free to reach out to me on my Twitter, which is there. Okay, so I can see a couple of questions here. Thank you so much for commenting. Is there something similar to MicroProfile LRA for Spring Boot? Great question. I am not sure. Now, I know that you can run Spring Boot applications on stuff like Open Liberty, and there are some performance benefits, I think. So let me check that and see if you can use it or if there's an alternative in any way. I'll get back to you. If you want to reach out to me on Twitter, I'll get back to you on that and see if I can find out. Even though you don't seem to favor 2PC, is there a 2PC coordinator available for MicroProfile? So you wouldn't have the 2PC because you're not using ACID. So a two-phase commit coordinator is essentially there as a consensus protocol within an ACID model. We still use coordinators in MicroProfile. It's just not necessarily called a 2PC, I don't think, for example. But you can see in the example I showed, if I go back to the architecture of it, there we go, there's one. So you can see we've got an LRA coordinator, and that acts in a very similar manner as that central coordinator and gets all of the participants involved and stores the state, for example, of the overall transactions as well as the microtransactions. So it, as the name suggests, coordinates the whole thing. So that's what you would use really when you're looking at MicroProfile, and it depends on the implementation you use as to what's offered by that implementation. Oh, I've lost, there we go, play from current slide. Blah, 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 blah. The cancellation calls can also fail. What should be done? So in Saga, for example, the nice thing is that you're not locking any resources. So if you have a particular microservice that's, say, being really slow, your other microservices aren't resource locked whilst your overall transaction is waiting for that last, say, really slow microservice or communication failure, whatever it might be. And so what can happen is other microservices or other transactions can come in and utilize those microservices. So they're not unresponsive like they would be with an ACID model, for example. So that's where we're into a lot more of being cloud native, being available all the time, having performance at its best as much as we can by not having this sort of resource locking type of mechanism. So even though calls might fail, or for example, microservices might go down, it's in a lot more of a cloud native manner. And we're not sort of blocking anything else within our application from being able to use those resources or access those microservices. So it's a lot more dynamic in that sense. I'm afraid I am at time, I believe. So I will have to try and answer the other questions asynchronously, either through the chat or on Twitter if you want to reach out there.